Got it.
Hi everyone. I'm going to give it a couple more minutes before we see how many people we get in here. So just to let you all know kind of the rough structure for the course, for the tutorials. I'm going to be hosting, this is the first of 4, roughly every 2 weeks apart, going over each of the 4 topics in the Navigation Systems 4 course. So first going to cover mathematics. Next time we'll do inertial navigation. Then integrated navigation kind of towards the end of the course. Right, I've enabled live transcriptions. I don't know how that actually works, but if there are any problems, just let me know. This is being recorded, so that's quite cool actually. You can see it at the bottom. I'm going to upload it to Moodle afterwards so that you can look through in your own time, and for those that weren't able to make it today. So we're going to go through 3 questions from the navigation mathematics part of the course. Thank you. Got my eyes a little bit off topic, but right. So we're going to do 3 exam questions that I've picked out. So you only have access to 1 exam paper as per university guidelines. I'm going to go through some of the previous past papers examples as well. I'm not going to be uploading solutions, so do try and follow on paper and pen in your own time. But oh, hey, it's you. Sorry, Jeff, can't really remember meeting you. But the video is going to be online, so you can follow the transcription from there. You'll obviously be able to see me go through the sample solutions as well. So the three questions we're going to go through. First is going to be from a 2016 paper, question 1, which is, I'll put it on screen for you now to see. It's a fairly common not sharing. Right, can we all see this question on the screen? Just give me a hands up in the chats or an emoji. Yeah, perfect. So I'm going to go through question 1A first. Then we're going to move on to 2017 question 1, which is, I remember which one it is. Sorry, this is the first question we're going to go through. Then we're going to go through 2018 question 1B.
Oh, sorry.
Yeah. Someone have a question? See Zoom only. Okay. 2 seconds. I'll try sharing again. Can you see now? Yeah. And you've seen the questions? Yeah. Okay. So second one we'll go through is question 1B here, which is quite a bit of a shorter one, but that's kind of on direction cosine matrices, a little bit sort of inertial navigation, but it's sort of mixed together the first 2 topics. And then finally, we're going to go through this kind of long question, which is one of the trickier ones that's come up in recent years. But it's quite involved, and it will cover most of this sort of section of the mathematics part of the course. So that's why I picked it. Okay. So first one, we're going to do sort of the great circle distance question. There are a number of variations of different things that potentially can be asked. I'll kind of cover those as we go through them. But for now, this is kind of quite a basic one. So for now, I'm assuming you can all access, well, we'll see the question, but I'll flip between this and actually my working. But basically the question is asking, can we calculate the great circle distance from Glasgow Airport and New York? And it defines each of these locations in latitude and longitude. First thing to note is make sure that these are north and west. Sometimes these could be east and south. And if that's the case, then you're going to need to translate them to make sure they're in the correct format for the equations we're going to use. Okay. Right. So now let's share. Okay, so you should all be able to see my tablet here. So I'll jot down the key information on for the question. Okay, so we have Glasgow, which is given as the kind of coordinates. So 54 degrees north, 52 minutes, 19 seconds. Not sure you can all see that, yeah. Again, just shout out in the chats or someone pipe up if you can't see anything that I'm doing. Okay, and then the other coordinates. And again, kind of noticing that then north and west. And then we have New York as 40 degrees, 38, 24, and 73. So those are our 2 points from the question. Okay. Now we have the first thing we need to do is generate the sort of Cartesian coordinates of these points. So we're going to have 3 equations that we're going to use. They should be in the data sheet for you. So these are kind of in Earth-centered coordinates. And they are as follows. Cos, latitude, cos, longitude. Okay, and the same for Y and Z coordinates. So X and Y are fairly similar in terms of their equations. Z changes a little bit. And then same cos and then sine. Okay, make sure that's clear enough for everybody. And then our Z coordinate as well. So E is kind of the eccentricity of Earth, so we're going to use that a bit later. Because so basically it's a factor that makes sure that we don't assume a spherical Earth. Okay. Sine. Okay. So we have our kind of equations here, and we're going to first check our coordinates for latitude and longitude. So we know that they're in north and west, which is the desired formats we want. So that's these to make sure they're there. But in order to plug in with angles into our equations, we're going to need to convert from this sort of degrees, minutes, seconds formats and into decimal degrees. So you can do that on your calculator. So I have a Casio right here, and I'll be able to Google how to do it yourself, but there should be a button above where it says eng, and it's got a degrees, comma, and then speech marks. If you basically type in, say for New York City, the north kind of coordinate we have 40, 38, 24. If you put that in with the symbol in between and click equals, you'll be able to convert that to a decimal. Okay, and when we do that, so I'm going to write out Glasgow and New York again. So we have our longitude and latitude. So longitude being the one that's a west coordinate, latitude being the north coordinate. Subbing those in, we get these values. So minus 4.43331 degrees, latitude 55.8719. Okay.
Excuse me.
Yeah.
What button do you press like to calculate it? I got it in the calculator, but
so I'll try and get it close. I'm sharing the screen. That's not going to help, is it? Let me stop sharing and I will. I was on the wrong thing. Stop share. Okay. All right. If you put me to max size on your screen, so we're using this button. I might have to focus on it. 2 secs.
Yeah, the button that has a circle.
Yeah. So your degrees, minutes, seconds. So for example, if I do the Glasgow latitude, I'm going to put 55. I'll type this in and show you on the camera. 55, 52, 19. Okay, it doesn't show up as the separate, I know it's backwards on here, but if you put it all and press.
Yeah, for me, it just shows circles, and then when I press enter, it shows.
Yeah, and then if you press where it says eng, so the engineering button, that will change the units to decimals.
All right.
Okay, so it'll go from degrees, minutes, seconds back to then 55. So in this case, 55.81. So that's times 10 to the 0. Then it'll do times 10 to the minus 3, times 10 to the minus 6. So you're able to get it through that way.
But I heard like there is another formal equation, like you could do like 55 plus 52 divided by 60 plus 19 divided by 3600.
You could do that as well, yes. But we all have calculators, so I would recommend doing that and not wasting time on sort of basic math like that. But yes, you can do that. Okay, right.
I'm so sorry, but could you please repeat what exactly to press to change it into minutes and seconds, because I'm unable to do that on my calculator.
Right, I'm not going to run through everyone's run of calculators because we're going to run out of time. But for me, on a Casio, it's the button that says ENG, so engineering. You might have another button, but if you search how to convert degrees, minutes, seconds to decimal on Google for your type of calculator, then it will convert automatically. Or as the kind of previous student said, you can do it manually by adding on the minutes divided by 60 and the seconds divided by 3,600.
Thanks a lot.
Okay. And just in terms of kind of shouting out comments, I will try and answer as many questions possible, but just to make sure we get through everything in time, put them in the chat first and I'll try and answer them when I can. Okay. Right, back to the example. So you should be able to see now. I'm basically just filling in, I've done this kind of before, but I'm putting in the values that kind of I got out of the calculator. Again, think about when you work into an exam, the number of significant figures, try and do exact values or states. You're going to do four decimal places and use that consistently. You're not going to be marked down for doing either, as long as you state what you're doing. Okay. Now, so we need to calculate the sort of the transverse radius of curvature. So that's the REL value that we have kind of in these equations just here. Okay, so the way we do that is REL is equal to the radius of Earth over 1 minus the eccentricity sine squared and then our latitude. Okay, so we're only focusing on the latitude values here, so the north thing here. And that's one thing I struggle with, remember which way around they were, but latitude is the one that has north or south, and then longitude is the west or east. Okay, so from there, where we know that from the datasheet E is equal to 0.0818, we're basically going to calculate our Glasgow transverse radius of curvature and our New York one. So that's basically the radius of the Earth at each of those kind of points, each of those latitudes. Okay, so when I sub those in for Glasgow, I'm getting, I find it just here, radius of Earth, just so in case anyone doesn't know, it is on the data sheet, so you don't need to remember it. 6378137 meters. But subbing that on in for Glasgow, I'm going to get 6.392816 and times 10 to the 6 meters. And for New York, we're doing the exact same thing. These numbers will be very similar, so make sure you don't get them mixed up when you're doing your paper. 212 times 10 to the 6 meters. Okay, so we'll need those for our equations. Now, so we have our REL values, we've got that. Altitude is not going to apply to this example, but if you were looking at, or if the question asked something about a helicopter or an aircraft above that example, here is where you put in your altitude. So say if we're, I don't know, 10 kilometers above the Earth's surface, we'd add in that there. But as we don't need it just yet, that's fine. Then we also have our latitude and longitude there. Okay, so we have everything we need to calculate the coordinate positions of Glasgow and New York with respect to the Earth and resolved into the Earth coordinates. Okay. So just in the kind of process of time, all you're going to do is sub in your values into those equations, making sure that for Glasgow, we're going to use this REL value. And for New York, we're going to use the equivalent transverse radius of curvature as well. Okay, so subbing those in for X, Y, Z, I'm just using this notation for ease of speed. Okay, that's resolved into Earth frame with respect to the Earth frame, and we're looking at the body frame. Okay, no, so our REL with the bracket in there is just the transverse radius of curvature, so you don't need to add in latitude into there for that question that came up. But for Glasgow, I'm getting 3575927 meters. The Y value is minus 32055 meters. And Z 4966803. Okay, so that's GLA and then New York. So New York, Similarly, same process, just again,
Is that
swapping
minus 36055 or minus 32055?
3, 2, sorry, my handwriting's dreadful. Okay. Try and be a bit clearer from now on. And then when we do the New York ones, same again, same process. Again, these are very similar throughout the exam papers. But again, I'm going to throw in the kind of the extra bits you need to kind of look at potentially or that have come up previously. And then the Z coordinate 4132168 meters. Okay, so we now got our 2 points on the sphere. So GLA and over there somewhere, New York. And we want to work out this distance, this great circle distance between them. So that's, imagine in a sphere, that's the shortest distance between the 2 points on the surface of the sphere, so confined to that surface. Okay, now we can't just assume when we've got these 2 points, we can't just work out the distance between them. So usually you just do a simple subtraction to get the vector between those 2 points, and then you could take the norm to get the length of that point. Now, because we want it to curve around the Earth, we first have to think about the curvature. So we do this by using the scalar products and the angle between the 2 points. So the scalar products for 2 vectors is equal to the magnitude of those 2 vectors multiplied by the cosine of the angle between them. Okay, so fairly straightforward there. We know that we have these 2 vectors, which are given by our x, y, z coordinates. So for Glasgow and New York, so let's call Glasgow A and New York B. Now, if we then calculate the dot products on the left-hand side, and then, so again, in the interest of time, I'm not going to go through the actual calculations, but you'll be able to check this yourselves. Equal to cos theta. We take the inverse cos, and that will give us our theta, okay? Where A is equal to the Glasgow coordinates, B is equal to NYC coordinates, the modulus function or the norm being the square roots of the squares. So pretty basic on that front. But when we work this out, we're actually going to get an angle of 46.5910 degrees. Okay. And that's imagining the center of the Earth as the origin, the 2 vectors coming out from the origin going through each of the points on the surface. That angle now between those 2 vectors is what we've just calculated. Okay. So A and B are just these 2 vectors up here. So A is equal to x, y, z for Glasgow, and same for New York. Okay. Now, a case where you wouldn't need to think about this is, say, think about an airport. So say we wanted to work out the distance or the length of the runway on an airport, and we have the coordinates of the start point of the airport, or sorry, start point on the runway and the end of the runway. That distance is so small in the scheme of kind of the Earth that you wouldn't really need to consider this. You'd get an angle so small, kind of fractions of thousandths of degrees, you wouldn't need to consider it. So have a think about what the question's asking you and whether you do need to consider this. But all we need to do then is we have now, I'll kind of draw this quick little diagram, an arc where we want this distance. We have theta, and we also know kind of the radius, the circumference of the Earth, which would be around here, where the circumference is 4003.2 kilometers. And we can then do a really simple, basically, what sector is that value of round as part of the Earth's kind of sphere, to get what our great circle distance is. So to do that, so great circle distance is do equals rather than that. is equal to the fraction of the circle, so this of the Earth, so theta over 360, and then we multiply that by the circumference. So to get that final answer, we do our angle, which is 46.5910 degrees over 360. Again, if you've calculated it in radians, just change that for 2 pi, they're interchangeable. And then multiplied by, and that'll give it in kilometers. And then we should get approximately 5180 kilometers as our final answer. And that's the Great Circle distance between Glasgow and New York. So this is the bit where it's taking into account the curvature of the Earth at Elias. So again, if we're looking at 2 points in Glasgow, say the Great Circle distance between, I don't know, Glasgow Uni and the train station, you probably don't need to consider it there. And all you'd work out is just the flat distance between the 2 points. But because we've got a curve, and this will be the case in most exam questions, you need to consider kind of the curvature of Earth in this sphere. So that's why I've done this little diagram of the Earth here. Okay.
Do we have to care for the X and Y coordinates that they're in meters and not in kilometers, or it doesn't matter because we're dividing?
Doesn't matter, as long as you're consistent, you don't let it change and you write your units at the end, that's all that matters. Okay. Right, I'm going to move on to the next question. Again, this is going to be uploaded, so you'll be able to view everything additionally, just because we are running out of time a little bit. So we're going to go on to question 2018, question 1B. So I'm going to stop share the, sorry for the rush, guys. We don't have that long. And we're going to do 2018B. So. Okay, so question 2018B, position of a fighter pilot seat relative to the aircraft center of mass resolved in the body axis, denoted by LBBP, show that the speed experienced by the pilot during an acrobatic maneuver is given by this equation here. So a simple show that question, so basically proof, working through it and showing all the steps that we get to this final value. Okay, right. So how do we get there? So we need to calculate the velocity, which is r dots, of the pilot relative to the kind of inertial frame, and then resolved in the body frame. Okay, because the body frame is what the pilot's experiencing. So it's always helpful to start in defining what this actually means. And we do that by looking at the equivalent inertial parameter, so resolved into inertial frame, and then looking at what coordinate direction cosine matrix, what transformation matrix do we need to get it back into the body frame. And that's very simply CIB. So the transformation matrix going from the inertial frame to the body frame. Okay. Now we can also, that's what we kind of need to get at overall. So we're going to start with this value here. But obviously we're going to start from a position rather than a velocity. So we have R of the body. So that's the position of the body relative to and resolved in the inertial frame. Sorry, that should be the pilot, not the body.
Why are we using the inertial frame and not the Earth-centric frame?
Because we want the velocity of the pilot with respect to the aircraft center of mass. So this is the inertial frame is the body, is the aircraft in this point, because the aircraft's moving around, the body being the pilot. So if you tried doing it in the world frame, which you probably could do, the Earth-centered inertial frame, it's going to be very big, and you're going to have a lot of rotations to factor in. We're just doing what the question is asked in this example. The second example I'm going to go through after this is going to be much more involved, and we'll go through multiple different types of rotations. Okay. So we want to know firstly the position of the pilots, kind of in the inertial frame, and handling the question, it's actually given to us that it's the position of the body frame, and then plus we have this length in here. Okay, Now, we can't directly add this length to our previous position here because we're resolved into different frames. So again, we need to use a direction cosine matrix to go from body to inertial. Okay, so body to inertial. And that gives us basically our rough geometry for the position of the pilot. So basically all we need to do now is take a derivative. So with respect to time. And that will give us here. Now, the first bit's really easy because all we're doing is to differentiate a position in the inertial frame, the body. So B, sorry, I'm getting all these letters mixed up, B. So the first part. And then we need to use the product rule to differentiate the direction cosine matrix and our length. We'll use the product rule, but as you'll see, the length's constant so that the change in length is 0, so we can remove it, but I'll do it for clarity anyway. So differentiating the direction cosine matrix first, we get C B to I dots with our length, and then our second term, I'll put this in brackets just for clarity. And I would, if you had asked a question along these lines, include this because it shows that you sort of know what's happening. Obviously, if we have a constant length, then the rate of change of that length is going to be 0. So this will go to 0. Okay. Right. The eager-eyed amongst you will have noticed that given we now have basically up to here, we have a derivative of a rotation matrix or a direction cosine matrix. So we're going to now use what's called the strap-down equation. So you'll have covered that by now. It's in the data sheet, so you don't need to learn it, but there are 4 forms of it that we're going to use. We're going to go through it later in the final example a bit more in depth. Basically, we need to pick a term of the strap-down equation that matches to our derivative here. So we have C I to B. Okay. And the final bit of information we need to take from the question is that we're going to, because we're using the inertial frame, we're using a gyroscope to measure the angular rates. And gyroscopes, so I'll write this down. So gyroscopes measure, get this right. So the body reference to the inertial frame resolved in the body frame. And when you're using these with rotation matrices, we use something called the skew symmetric operator, which is basically taking this sort of vector and turning it into a 3x3 matrix. Okay, we don't need to do any of the maths for this at the moment. We're just going to call this capital omega with the same notation. So we need to find now a form of the strap-down equation that has these 2 values in it. Okay. There'll be an equals here, and we just need to basically work out what is this direction cosine matrix and where is it in our system, in the equation. Okay. So the form we're going to use is C dot IB is equal to CIB omega BIB. So this will be written in the data sheets as C alpha Bravo, C alpha Bravo, Bravo alpha Bravo. There's 4 different versions of it. This is kind of known as the gyroscope term, just because it's generally used in sort of inertial measurements. Okay, so we want to use this and sub into our equation over here. So when we do, we're going to get this. We're going to sub in CIB, we go BIB. This here. So 2 things we can look at now. Firstly, this term on its own, it's the velocity of the body respect to the inertial frame. this is typically referred to either as sort of UIB or VIB. So you can replace it for one of those. The form we need, it's in, if I just check, is the, sorry. We'll do that later on, actually. Sorry, we're getting ahead of myself. So we have this kind of final form. Now, if we go back to right to the start, we just defined our correct value we need to get up here as the velocity of the pilot in the inertial frame with this direction cosine matrix. So we need to add one more direction cosine matrix to the whole thing. So to get back into the body frame, we need to do one direction cosine matrix and then multiply the whole expression here. Now I'll expand that out. So we get CIB. You can see the bit where I got ahead of myself just then. We have CBI, CB. Okay. So the first thing we note, we have here direction cosine matrix going between two frames, one forward, one backwards. So when we're doing that, that just equals 1. Okay, because it's basically the inverse or the transpose of the matrix multiplied by itself. So it's equal to 1 for normalized rotation matrices anyway. And finally, we have this little guy here. And all this is doing is we're taking our velocity from the inertial frame to resolving it into the body frame. Okay, so that gives us VIP is equal to R dot BIB plus omega BIB LBBP. Where this is where I got ahead of myself, where we refer to this as sort of got the line there, VBIB, sometimes referred to as sort of UIB as well. So if you see that anywhere, that is basically the velocity of the body in the inertial frame resolved into the body frame. Okay, now if we add that in to our final result, plus omega BIB plus the length BBP. We get to the solution just here. Okay. I'll stop for a moment and go back to it. I will go back to it in a sec just to show the thing here. So as I said, VBIB, or it's known as UB as well. And then we have our skew symmetric angular velocity matrix in there as required. Okay, so that's quite a common sort of question. It's quite a short one, so it might be tagged on to the end of a different topic, but it's a fairly kind of brief example. Right, I'll quickly go back to the solution just in case anyone was still writing that. And then I'll go through some of the questions that we've had. So the reason for choosing our initial R up here is the body is the aircraft, so we want the position of the pilot relative to the inertial frame resolving the body frame. So that's what we're looking for. The reason why we chose this is because we want it to be relative and resolved into the same frame. For situations where you can assume no angular velocities, you don't really need to make that assumption, but because we're unsure about it, we need to include this direction cosine matrix here as well. So this is again, so Lisa, you saw that V is not necessarily equal to R dots, that's true. But in this case, for R dot in body frame inertial resolved into the body frame here, we can make that assumption for that one. But when it's asking for velocity, it is asking for an R dot. So you can't just do that. You can't just do that for this one for example. It's only kind of an inertial case for this one.
But if you go back at the beginning of the exercise, it's not the same resolving and reference frame. When, like, if you can go up.
What was that, sorry?
If you can go up at the beginning,
Yep.
when you just put air dot, yes,
Yep.
here, you don't,
So I don't, yeah, so I don't do it here. But this again,
Okay,
it's really not. So I mean, the correct term is to have it as an R dot. It's just that this part of the question is checking that you've listened to the lectures where I believe Dr. Anderson goes through that in aerospace applications, they sometimes use this UB or VBIB term.
okay.
Okay.
Okay, I think in the worked example, at the beginning of the exercise, it was written V equal air dot, so that's why it was weird. Even when the reference, yeah.
Yeah, that's fine. Again, so it's not really, again, if you put it to this point, you'd get pretty much all the marks for example. It's just this little sort of thing showing that they're equal. It's just something that's come up in the notes. Right, got 20 minutes left. I'm going to go through the kind of most in-depth question. This is one of the most trickier ones, or longer ones anyway, that have come up in recent exam papers. So I'll just quickly share what that looks like. Okay, so it's with reference to the simple coordinate system diagram in figure 1. So kind of inertial earth frame at the bottom, body frame, which is the helicopter, rotor hub, which is H. So that's kind of the center part of the hub where the blades are rotating around, and then P, which means kind of the point on the blade tip. So we need to show that the absolute velocity experienced by point P is this kind of horrible equation down here, given all these frames and the kind of moment arms between them, so these L values. One important thing to note straight away is what angular rates we have to consider, because this is going to show us what forms of the strap-down equation we need, and what forms we want our coordinate direction cosine matrices to be in. So we have omega BIB, which is kind of our gyroscope, the rotor hub, which is the basically angular velocity of the hub with respect to the body, so how fast our rotor is spinning around, and then the Earth's rotation as well. So this is going to be quite an in-depth one, but we'll walk through it. Okay.
Which year's paper is this?
This is 2017, so I don't believe you have this one either as a mock exam. It's quite a lot longer than all the other similar questions in previous past papers. That's why I wanted to go through it, because this is really the longest it could be.
Okay.
Right, so can we all see that now? Then I might have to skip a couple of steps just in to make sure we can write everything. I mean, I'm happy to go past 6 o'clock if people have questions. So, but we'll try and get through it as quick as we can. So the question also hints that it first would like you to define this parameter. So the point on the hub inertial frame resolved into the Earth axis. Again, we're going to follow that similar first step of taking it from the Earth-centered Earth fixed frame to the inertial. So again, we're going to have our direction cosine to get here. Okay. As we have all of these angular rates, we can't just assume that the velocity can be rotated with the angular rate. It doesn't kind of work like that. So this is how I have to kind of do it from first principles. So next part then is trying to work out what is RIIP. So we're going to leave this cosine direction matrix in. I won't kind of just work on the inertial frame for the points and then add on the cosine matrix at the end. We'll work through it all together. So we eventually want to expand this. And if we look at our diagram, similarly, we're going to have the previous inertial position, so RIA, but not the point this time. We're now going to have the hub. And then we also have this moment arm between it with a direction cosine matrix. So our moment arm L is LHHP. And again, rather than respect to the hub, we want to be in inertial frame. So we're going to put this direction cosine matrix in. Now you'll remember that we didn't really have any angular velocities or terms in this format. So this is where you need to be kind of a little bit cheeky and look at the sort of the solution, or so look at the final answer and also what information we have, so angular velocities, so we can work out what forms we need. And we need to actually replace this with a different one. So rather than having direction cosine matrix here, we're now going to split that into so not going to split it, we're going to expand it first, getting ahead of myself again. So we'll expand that out. So this should, for now, look very similar to the previous example. So CEI, CIH, oh, HP. Okay, so we'll keep that for now. We're also then going to finally, because we've got one other frame we need to look into, we're going to change or do our final thing. So we've currently got the position of the hub. We also want the position of the body. So we're now going to expand this again. And it's the same process no matter how many frames you have. So you could go on for 10, 15 frames, do exactly the same thing, replacing these and then getting the direction cosine matrices in the same form. So then I'm going to replace it. So if we look at our diagram again, the next frame is the body, and we have a second moment arm of LBBH, so between the hub relative to the body, resolving the body frame. And again, we're in the inertial frame, so we need a direction cosine matrix from the body to the inertial frame in there. And then we'll just bring down what we had before. And I think the eagle-eyed among you will have seen that you can actually simplify this direction cosine matrix just here, because one's going from hub to inertial, the other's going to inertial to earth. You can just basically simplify that to hub to earth, but we want to keep that for a very specific reason a bit later on. So I'm going to leave that there. Okay, expand it one more time to get everything sort of in our sort of position form. Okay, and we'll be left with that. So now we need to do a little bit more trickery. So, oh, don't want to do that. Looking at this, we have an angular velocity for resolving the earth frame, the inertial frame. So that's fine, but we don't have anything for this IH term here. So we need to do a bit of wizardry to try and get that into a form that we do want. So we'll note that CEI, CIH can actually be written as okay. Over for that step. So we've basically turned direction cosine matrix from the hub to the inertial frame into the direction cosine matrix from the hub to the body, and then body to inertial. Okay. And now if we look at kind of our subscripts and superscripts, we have an angular velocity in the earth fixed frame, We have one for the body, which is our kind of IMU gyroscope frame, and also the hub with respect to the body. The hub with respect to the body being how fast we're rotating around, the rotor rotating around on the helicopter. Okay, so that's the key bit of information, or kind of key little trick that's kind of put in there that you need to be wary of. So we'll write this out once more. Again, I've expanded it out just to make it easy to differentiate a bit later, but you can keep it sort of a bit more segmented if you want. And then add in what we just kind of worked out just then. And now if we look through our equation here, we've got EI, inertial and body, got EI again, got IB, which is our gyro term in the strap down equation. We're basically trying to get our direction cosine matrices in a position where when we differentiate them and get a derivative, that we're able to use the strap down equation effectively with the angular rates that we've been given in the question. Okay, so look at the subscripts in the angular rates and match them to the direction cosine matrix. And if you need to kind of expand, contract these direction cosines to make sure they're in the correct form you need. Okay, but carrying on, we've got EI, we've got IB, and we've got BH. So these are all angular rates that we have. So now we know that when we differentiate and use the strap down equation, we're gonna have to use multiple forms of it. We're going to be able to correctly pick the right ones out and sub it all in. Okay. So same process as the previous question. Taking a derivative. And there's going to be a lot of product rules. It's going to be quite a long things, but we'll get through it all. So first product rule, put these in brackets to sort of separate it out for when you're writing it. Okay. Again, this little thing from last time, you'll sort of remember that little trick we did, converting it into the earth frame, and then again, that's sort of known as a velocity and it's another name or another letter. So I'll let you work that one out for where that's going to go. Second term, we're going to have three terms. Again, we've got an L constant, we're assuming a constant angular arm or constant moment arm. So when we do a derivative of L, so L dots, that's just going to go to 0. So we're really only going to get two terms here. With a dot there. And I'm going to leave the last one in that just because, again, it's self-explanatory from the previous example that we don't need. We can cancel out the fact that it's going to go to 0 when we try and differentiate a constant value. And I'll go underneath final bits for the last one. We've got 3 direction cosine matrices, 3 product rules. So we're going to have 3 terms. Again, we're going to have C dot EI, CIB, CBH. Okay. Final one. Okay, and that's our differentiated equation. Make sure everyone can see that. Okay. Right, as previously said, we need to look at the angular rates. So in the skew symmetric forms where omega is equal to skew symmetric or wedge operator, sometimes it's denoted as a sort of wedge like that. Basically, it's taking a 3 vector into a 3x3 matrix. It's actually got some nice manifold properties for anyone interested, but I doubt we are. So we have 3 angular velocities. We have, this is our first one. Second one being the gyroscope, what measurements, kind of what a traditional sort of strap down system will measure. And then our third being the angular velocity of the hub with respect to the body. Okay. And similarly, we have, if we look through, we have a C dot EI term. We have a, let me find one, C dot IB. And then we also have a C dot BH, just on the kind of the far side over here. So we need to look through the strap-down equation and see what forms we get from this here. So to save time, we have the first one we used last question. So CIE is equal to, well, it's slightly different actually, minus omega okay, should be a dot there. So for number 2, which we did use last time, sorry, I got them mixed, which around we got mixed up. So we have C dot IB is equal to CIB, and then our angular velocity just here. Is everyone following me so far? I've not had many questions. Sorry, that's me doing a very good job or a very bad job. Or is it just over everybody's head? And then finally, going from the hub to the body frame, the derivative there, we get, and looking at kind of the way we have our B and H, we get these. So these are the 3 strap down forms we're going to use. Again, the way to do that is you look at, okay, which order, so C dots, so we've got alpha, bravo, top and bottom, and you basically need to look through which form has, for the omega, has alpha, bravo, alpha for this one. That's how you go through it. In the data sheet again, so you don't need to memorize it.
But why did you choose the negative? The minus?
That's just one of the forms of the strap down equation. If I find this for you. So strap down equation, we're using, let me work out. So this is our gyroscope form. This is our hub to body form. And then let me get this the right way around, which one it is, this one. That's our inertial to earth centered earth fixed form. It just happens to be a negative. Basically, when you do the derivation with respect to it, there's a proof in the book that's recommended for the course if you want to really torture yourselves. But basically, these are the kind of the 4 forms that pop out for different resolving frames when you do it. Okay. Again, so hard to see on the screen, but basically we're going to take our equation we had before with our C dots and sub in what we just got using our angular rates and the strap down equation. The strap down equation is basically an expanded form of rotation matrix propagation, how you work out of the differential equation for rotation matrices when you have an angular velocity acting on it. But again, we won't really go too much further into the course. Right. So we have everything we need now. So we're always going to be subbing in and some rearranging to get it in the form we want. So I'm now subbing in, again, we're looking at the first bit here. So we have a C dot, and I'm now going to sub in this version whenever I see that. Okay. So CI. IB plus, and some of it we can just carry on through because there's no derivatives of direction cosine matrices in it. Okay, so that's the first one. Second one, we immediately have this this value again, so we're going to put that in, and again we're going to get a negative angular rate with direction cosine matrix multiplied by length and plus our second. I'm missing a matrix there, aren't I? CIB. Again, we'll see a little trick there. So if you look at the final form, again, if you have to scroll back through the video, I'll put it up in a little bit. We don't have a term CIB. So basically we can just change this to equal to CEB. So that's body to the earth fixed frame. And that's just basic matrix or navigation matrix multiplication. So continuing on, we get CI. I want to CIB using this one now. Omega BIB. LBBH. Okay. Then for a final one that has 3 terms, I'll put this right at the bottom. Just get a bit painful to keep writing all of it.
For the H frame,
Yeah.
do we consider it like rotating about B?
Yeah, so that's where we're going to have that in the last term. So yeah, it's rotating with respect. So the hub's rotating with respect to the body. And we've not assumed, well, we are assuming the Earth rotating, but we're not assuming the helicopter body rotating with respect to the Earth at the moment. So that would be a Omega B EB.
So that's why it's not minus.
It's not minus just because the strap down equation isn't negative for that. So if you're going to do reverse this, sorry, I know you can't see when I'm pointing. If you're trying to reverse this and have the angular velocity of the body with respect to the hub, then these values would basically flip around. And if you had a B.H, then a negative sign would come out in there. But then again, that's a little bit beyond what we're going to be studying.
Okay.
Okay. So 2 terms left. So CEI. Now we're looking at the gyroscope version. We again CBH again. And then we have the moment arm of the point from the hub. And the final term, again, we have this term which we can call CEB a bit later. We have Omega BBH, CBH, and again, finally, our moment arm for the point to the hub. Okay, so I put brackets around them so you can see where they come from in relation to the sort of the 3 bands of terms we had before. So just in interest of time, I'll write the answer down and I'll kind of show the bits where we come to. So for here, that's very simple. That's basically just equal to what we had before. And then again, you can call that sort of U, which is kind of typical notation for aerospace applications. We're going to cancel these and call them CEB. So body frame to the Earth, center Earth fixed. Basically just combining those direction cosine matrices to make it a bit neater. Again, we can do the same thing here. Here, there's a lot of cancelling involved again there. Okay, and then once more down there. Okay, so that gives us do one more step actually, just to make it a bit clearer. Okay, here we've just used the direction cosine matrix, turning the resolving frame into from the inertial into the Earth centered Earth fixed. So that removes that one. Plus we now have our quite common velocity term on its own. Earth body. Change that one. We've now changed another. Now again here, you should be able to see that we can actually simplify this into CE from, so transferring from the hub to the Earth-centered Earth fixed frame. Well, given that's not in the answer, we're going to leave that one, simplification. And then the final term, CB, and we go BBH, CBH. And then basically to finish off the question, we just have a little bit of rearranging to do. So we're going to take this first term out just because it's sort of on its own with nothing there. So again, equal to UB sometimes, basically the body velocity with respect to the Earth. So basically how fast the helicopter's traveling. Then we're going to first take out, if we have a look through kind of what's quite common, we have this, the angular velocity, or basically the rotation of the Earth cropping up quite a lot. So first we're going to take that one out. We'll take out the negative sign as well, because that sign comes from the strap-down equation, so it doesn't appear anywhere else in there. So I'm happy to take that out of the bracket. So going along again, so first we have this position. And then moving along, if we now have two terms that use that angular velocity and the CB direction cosine matrix, so we can take that direction cosine matrix out, and then we're left with basically two moment arms. So moment arm of the hub with respect to the body frame, and then from here, we have this term as well. So hub to the body, making sure that we can add those two moment arms together. That gives us our first parts. Okay. Then so let's have a look. I've not really shown the solution or the bit we're working towards that much, so I'll just put that on the screen just so we can see. Okay, so we have this first bit quite nicely. We just need to get the final bit. So here we want to take out our direction cosine matrix for the body frame to the Earth-centered Earth fixed, and then we should have two different angular rates, which we do. So our gyroscopic angular rates, and then our hub with respect to the body. So we're going to get it in that form. Okay, so if we take out this value, we have, I'll do a different color so it's easy to see. That's a bit big. So we have one there, one here, and that should be it. Okay, so we'll use the gyroscopic one first. That's this sort of whole term there first. Again, I'm making it as a bit harder than it seems, because obviously you're just trying to get it in the form that's been asked in the question, whereas I'm sort of doing it when I can't actually see what the form of solution should be. So we have to take out our BIB there. I'm missing one term, yeah. I forgot to add a term in, haven't I? I'm missing this one. That should be down there as well. Wondered why. So taking BIB out, we have two factors with it. So we've got this here, which if we take out the BIB term, we have direction cosine matrix from hub to body with the moment arm of the position of the point P with respect to the hub. And then we have the hub with respect to the body as well. So we'll do the same format as we did just down here. Okay, you'll just see some very sort of similar structures appearing in navigation systems in the solutions. So that's the hub with respect to the body. And then we take from up here, final bit, hub to body, our moment arm of the points with respect to the hub. And then the final bit we have is our little bit down here. Okay, so we've already taken out the direction cosine matrix, we now just have an angular rate, a direction cosine, and then a moment arm. So we'll just basically add that on to the end. And remember, and all that's multiplied by that cosine matrix, so we have to add our brackets on the end. Okay. And then, yeah, the final spot would be just to name that as UB. Basically, if you have a velocity of the body in the inertial frame with respect to, resolved into the earth-centered inertial, basically that's just a kind of a speed velocity in this instance. So we can do that. Okay. So that gives us our full solution. Okay. So it's quite involved. Again, that's a 20-mark question. So basically a third of your exam, because you're only going to pick 3 questions out of the 4 to do. But when you get the hang of it in the practice for working out what forms your direction cosine matrices should be in, and then making, well, by using the angular rates to inform what those forms should be, then using the strap down equation, picking the correct form of it, subbing it all in, it's not a particularly kind of difficult problem. It just takes quite a while. So main key to remember is that, again, the hint is what should you define your rotation, your kind of initial position to be, and make sure that you're taking a direction cosine matrix out and putting it into the inertial frame. That's kind of a good place to start. And then basically that just follows through to make sure that you're getting the correct strap down equation. So getting the C dots inertial to the earth-centered inertial, earth-centered earth fixed, sorry, which we know we need because we have the angular rates. So if you're going to go through this and kind of a worked example to work out what you need, sorry, so I have a question. I'll answer that question in a sec. Look at your angular rates first. So we know, wrong pen. We know we have access to these and we need to consider those. So therefore, we're going to have strap down forms similar to these. They might be the opposite way around, but they'll be similar to that. And then work out, okay, how do you get to those points? Sometimes you'll need to split a direction cosine matrix into 2 constituent parts and add in sort of a dummy frame in between. That's where we go from, in this part here, we've sort of added in the body frame as a dummy frame. Because really, sorry, wrong letter. Here we don't have any mention of the body frame, but given that we need to have the angular rate in measured by the gyroscope, which is omega BIB, we know that we need to add that in. So that's why we split it. Should it be wrong way around? IIB BH. Right. So questions. Oh, thanks, Nandi. Sorry, I didn't see the message. You missed the term. Yeah, got there in the end. Can you explain the first step in the second and third problem? Why are we taking this? So do you mean this step here? It appears. Yeah. So you want to define your, when you're doing adding so moment arms, for example, you want them to be in the inertial frame. Is it an instrument value? Do you mean why we want to calculate this, or why do I put it into the inertial frame here?
Yeah, that's the, yeah, I'm asking, I have the doubt in that thing. Am I audible?
What was that? So, yeah, I'm here.
Yeah, I want to know why you are taking RIIP, because in the previous problem you have taken the same thing. Is it an like instrument value or fixed value you're getting from the instrument, something like that?
It's not instrument, but if we have the origin at this point here, sorry, then we have a moment arm here. We don't want to add this onto a frame resolved in the earth-centered fixed frame. This is kind of an inertial thing, so we want to add it onto the inertial part. So that's why I put, if we have it in any moment arm, we want to make sure that we're adding it inertial frame. So basically, our IIP is the point, is the point of the point P in its own sort of frame. To get there, we're going to move from the hub, which is a separate point in its own frame, but we need to make sure that everything else is in the same one. So by doing that, it sort of, we're following a step-by-step process of adding moment arms where they are in sort of respective geometry, rather than trying to add everything into this sort of convoluted fixed frame.
So it's like a basic step for every problem, right? That we need to do it from the inertial frame.
Basically, yes. It's
And I want to know whether it's a
it-
basic step. We need to start for every problem from that
Yes.
point.
Yes,
Yeah, okay then,
it's a local frame. So when we're adding anything local measurements, local moment arm values, we're using that to add it on. Okay. Now, I saw another question, where can I practice this sort of stuff? This is the most intensive problem that has been in a previous exam. So there aren't any tutorial questions kind of like this, but there are smaller ones. Kind of this problem 2 that I went through was kind of a very typical exam question. It's only in one paper that had this sort of intensive process in it. But the tutorial papers, even some of the work examples that are in the lecture notes, they are very similar to what comes up. This was kind of just, this one threw quite a lot of people off when it was put in the exam. It was the year above me that did it. And you can actually look at, I believe the feedback for each exam is on the Moodle. So you can look at Dr. Anderson's feedback for the students that took the exam.
Sure, thank you.
Okay. Right, are there any other questions? I know we overran a little bit. This is how I'm going to basically run the next 3 tutorials. I'm hoping to do a 5th one as well, which will be sort of a more exam prep one before your exams. So I'll try and answer any questions if you email me. I'm not going to send my email just yet because there are like 280 students on the course. And I'm don't have the time to answer that many emails, but I'll make sure that Dr. Anderson passes it out if he thinks that's appropriate in the next lecture. Okay, so the next lecture is going to be inertial navigation, which features some of those similar sort of frame change, direction cosine sort of questions. Mainly it's kind of looking at accelerations, so a little bit more in depth, but there won't be any longer problems than the one we just did then. Date for next tutorial, it's going to be in 2 weeks' time. I hope to keep it the next same Tuesday. I will send a link out onto the notification, on the announcements on each of the Moodle when I've worked out when those are going to be. Yeah, sorry for the late notice for the 4th years. I assumed that the Moodle announcements would go between both of them, but they didn't. So I'll know that for next time. Again, apologies we couldn't get it timetabled. Generally, there isn't a tutorial session for this course, and Dr. Anderson usually just goes over one of the lectures and does a couple of questions, but I thought it'd be useful to do. And if it is, then thanks, let me know. And if you have any suggestions for things you want to go over, please let Dr. Anderson know in the lecture in terms of the tutorials, and I'll sort of factor that into what questions we do. Okay. All good? Right, so in that case, I'm going to end it and I will upload the Zoom at some point tomorrow. So you can go through this video again up until exams. It'll probably be taken down after the exam, just for whatever privacy reasons. But any questions in the meantime, just let me know. Okay. No problem. Have a nice evening.